Hello, hello. So in this video, we are going to discuss binomial coefficients and identity. So this is section 6.4, and we're going to cover the binomial theorem. First, let me give some motivation for the binomial theorem, and I'm going to do it by, and I guess I can leave this up here. I was practicing before making the video. I guess this is good. This will kind of save time. So suppose we wanted to just expand x plus y cubed, right? So we would write here that x plus y cubed is equal to x plus y times x plus y times x plus y. Now, how do we figure out what that is? Well, we would multiply x plus y by x plus y. That gives us these four terms, right? So x times x is going to show up here. X times y shows up here. Y times x shows up here. And then y times y shows up here. And now this is going to be multiplied by x plus y. Yeah, so we can say equals. Okay? And then we do the same thing. This times x is going to give us this term. And now I've got yx times x is going to give us yxx. And then xyx. And then yyx, right? And then I'll have xxy, well, yxy, xyy, and then yyy. Yeah, so I'm adding up all of these terms. And the next phase, what we always say is collect like terms. Remember how we say that? Collect like terms. Well, in our case, what that means is essentially group together yxx, xyx, xxy. Notice what we've done is, in getting these 8 different terms, we're looking at this set x comma y, and we are choosing 3 elements where we can repeat. So the first element is an x, second element is an x, third element is an x, then we get this term. But maybe we have xxy, maybe we have xyx, maybe we have yyy, right? So we're getting 8 different terms because we're looking at the number of ways to choose the number of, basically we're looking at the number of, it's very similar to when we're looking at bits, right? When we're looking at bits of length 3, right? 3, and then we're deciding how many x's and y's to have, right? Before with bits we had zeros and ones, now we have x's and y's. And when we collect like terms, what we're doing is saying that really we don't care about the order. So x, xy, and xyx are combined. So really we're talking about combinations. So in general, if I have x plus y to the n, right, how do I figure out x plus y to the n? Well, this x plus y to the n is going to be a sum of strings of length n, right? And then each part of the string is either an x or a y. So if I have all x's, now I'm going to simplify that and write that as x to the n. If I had like one y and the rest are x's, right? That would be x to the n minus 1 times y, yeah? So that's the left-hand side. And then the right-hand side is basically saying count in an organized manner the number of ways to have strings of length n, right? So if you have a string of length n, you have some number of y's, and the rest of them have to be x's. And we can count based on the number of y's are in our string. And now we're saying, how many strings will you have with exactly ky's? Well, that's our n choose k. So the number of strings of length n with exactly k y's, right? And now we're saying how many, we want all of the strings, right? Well, you can have 0 y's, you can have 1 y, you can have 2 y's, all the way up to n y's. So add them all up. This is really the addition rule. So that's the motivation. This is a statement of the binomial theorem. We've really just given a proof, and we see why the n choose k is our binomial coefficient. And just recall that we have this notation for the combination here, n choose k, and it means n factorial over k factorial times n minus k factorial. So that's what it means. Now let's go through and do a couple of examples just to show how to work with this equation here, how to work with the binomial theorem, and then we'll get a little more advanced and we'll actually start proving identities, okay? So for this first example, it's very simple. We're just going to expand x plus y to the 4th power. So we have our formula here. Right, this is our binomial theorem. And in this situation, we're going to let n equal 4. So k is going to run from 0 to 4. So this is k equals 0. What happens when k equals 0? Our coefficient, that one's going to be k equals 1, k equals 2, k equals 3, k equals 4. So we're literally just computing 4 choose 0, yeah, and that'll just be 1. 4 choose 1, that's 4. 4 choose 2, 6. 4 choose 3 is 4, and 4 choose 4 is 1. Okay, and then we add them all up, and there we go. And again, just to reiterate the connection we're making between the coefficients and the monomial, look here, what we're saying is that, what this means is that there are 4 choose 1, which is 4 different ways to write a string of length 4 with 3 x's and 1 y. And let's just double check if we can actually come up with 4. So I could have x, 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 y, x, x, y, x, x, y, x, x, y, x, x, x. Right, and these will all show up when I'm expanding that that term, okay? Okay, now let's go on to another example here. What's the coefficient of x to the 12 times y to the 13th in x plus y to the 25th? Again, I have my formula for the binomial theorem, And it looks like k is 13. So let's write this down. So n is 25, k is 13. Right, so the 25 is going to be 25. X is 12. Or sorry, n minus k is 12. K is 13. We're good to go. So the coefficient is going to be 25 choose 13. And then, we could simplify this, but 25 factorial over 13 factorial times 12 factorial. Okay. This one is a little harder because we want to know the coefficient, but this looks more complicated than just x plus y to the n. And indeed it is. What I'm going to do is I'm actually going to rewrite this formula as a. What if I rewrite this as a plus b to the n? So everywhere I see an x, I'm going to replace it with a. Everywhere I see with a y, I'm going to replace it with a b. And now, if I have this as a plus b to the 25th power, a is going to be 2x, b is going to be negative 3y. And 2x plus negative 3y, to the power of 25, according to my formula, is going to be 25 choose k times 2x to the 25 minus k times negative 3y to the power of k. And then k is going to start from 0. Start at 0 and stop at 25. So now, when I expand this, I'll have 25 choose k, 2 to the 25 minus k, and I'll have a negative 3 to the k, and then x to the 25 minus k, and y to the k. And now, x to the 12, y to the 13, k is equal to 13. So it'll be 25, choose 13, 2 to the 25 minus 13, times negative 3 to the 13. So this will be the coefficient. All of this is a coefficient of my x to the 12, y to the 13th power. Okay? All right, so we've done some examples. Now let's use binomial coefficients to prove some identities. And this first one here is proving this sum is equal to 2 to the n. So I kind of have a couple of different ways to do this. First way I want to do it is using the binomial theorem. So if I use the binomial theorem, then I can say that this left-hand side is equal to this if I let x equal 1 and y equal 1. If x and y are both equal to 1, then x to the n minus k is always going to be 1, and y to the k is always going to be equal to 1. So 1 plus 1 to the power of n is equal to the sum n choose k, 1 to the n minus k, times 1 to the k, as k runs from 0 to n. The left-hand side, of course, is going to be equal to the thing we want, which is 2 to the n. And the right-hand side is going to just be equal to the other thing we want, which is the sum of n choose k from 0 to n. So we're done. And there's a second way I can prove this. And the second way is using, right, our combinatorics more explicitly. So 2 to the n is the number of bits of length n. So the number of bit strings of length n. Okay? Now the left-hand side is going to be the sum of n choose k, k equals 0 to n. Now notice this is going to be n choose 0 plus n choose 1 plus n choose 2 plus da da da, all the way up to plus n choose n minus 1 plus n choose n. So each of these combinations, this represents the number of bit strengths of length n with exactly 0 ones. This one would be the number with exactly 1 1. This would be the number with 2 ones, right? So forth and so on. This would be the number with n minus 1 ones. And then this would be the number with n ones. And so just to make sure we're understanding and make sure you're understanding what I'm saying, let's look at a specific example. I'm going to look at an example where my n is not too large. Say n equals 4. Okay, say n equals 3, because 4 is going to be longer than what I want to do. Now, 2 to the n, the number of bit strengths of length 3. So I'd have 1, or I could have like 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0. 0, 1, 1, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. Okay. So 2 to the 3 is the number of strings of length 3. Now, if I'm adding up the sum of 3 choose k, k equals 0 to 3, this is supposed to be 3 choose 0 plus 3 choose 1 plus 3 choose 2 plus 3 choose 3. This is the number of strings with no ones. This is the number of strings with exactly 1 1. This is the string, the number of strings with exactly 2 ones. And then the last one is the number of strings with exactly 3 ones. Yeah? Make sense? Okay. So we're really, really, really emphasizing the connection between the subsets, and the bit string lengths, and, the coefficients in these that are being multiplied by the distributive property. Let's look at another example here. Suppose we want to prove this. Well, this identity can be proven. We want this to be over here. We've got to n choose k. Now notice we've got -1 to the k and y to the k. So let's let y equal -1. And if we let x equal 1, then x to the n minus k is always 1. So then binomial theorem is going to imply that this 1 plus -1 to the n is equal to the sum n choose k, 1 to the n minus k, -1 to the k, from 0 to n. Left-hand side is going to be equal to 0, because it's just 0 to the n. Excuse me. And then the right-hand side is going to be equal to this, because the 1 to the n minus k is always equal to 1. Okay. All right, so you see we can prove some identities definitely with, we can prove identities with binomial theorem, and oftentimes there are explanations that are more directly combinatorial in nature for the identities. For instance, here we can consider this as subsets, choosing subsets, or counting bit strings, okay, the number of bit strings. Let's move on to this identity. This is the last thing we'll cover. This is actually really cool. It's Pascal's identity. We're going to do 3 different proofs. The first is literally just using, algebra and working with the factorials. So let's start off with that. So now the left-hand side, n plus 1 choose k, is going to be n plus 1 factorial over k factorial times n plus 1 minus k factorial. So that's my left-hand side. And now what about my right-hand side? Well, the right-hand side is n choose k minus 1 plus n choose k. And I'm going to write that as n factorial over k minus 1 factorial times n minus k minus 1 quantity factorial plus n factorial over k factorial, n minus k factorial. Okay? And now I'm going to give myself a lot of space here to write. I'm going to get a common denominator. I've got a k minus 1 factorial and a k factorial. So if I multiply the numerator and the denominator by k, I can change this k minus 1 factorial into k factorial. All right, so I already have an n factorial in the numerator, a k factorial in the denominator. Let's go ahead, pull those out. What I'll be left with on the right-hand side is 1 minus n minus k factorial. On the left-hand side, I'll have a k in the numerator, which comes from this. And in the denominator, this is going to be n minus k plus 1. So n minus k plus 1. So I can rewrite that actually as n minus k plus 1 times n minus k factorial. And I now have an n minus k factorial in both factors, so I can pull that out. So I've got n factorial over k factorial, n minus k factorial. What remains is going to be k over n minus k plus 1 plus 1. So we're getting closer here. And I think what I want to do at this point is have my n factorial, k factorial, n minus k factorial, times, now let's get a common denominator. I've got n minus k plus 1, k plus n minus k plus 1. The k and the minus k cancel out, and I will now have n plus 1 in the numerator, n minus k plus 1 in the denominator, n factorial, numerator here, k factorial, n minus k, quantity factorial here. Notice that n factorial times n plus 1 is n plus 1 quantity factorial. And then in the denominator, n minus k factorial times n minus k plus 1 is the same as n minus k plus 1 factorial. And I still have that k factorial hanging out. Yeah? But notice I can rewrite this as n plus 1 minus k factorial. And now it's easy to see that this is the same as n plus 1, choose k, which was my left-hand side. So I've done one proof. I can do this proof without knowing any combinatorics. All I need to do is just know algebra, right, and no factorials. Let's do another proof. Another proof is going to be combinatoric in nature, which means we're going to, what does it mean when we say that a proof is a combinatorial proof? It means that the proof is going to show how something is true based on counting, okay? So, based on counting, this left-hand side represents the number of ways to choose k elements from a set of n plus 1 distinct elements. Another way we could look at it, if we've been doing the whole thing with bits, would be to say the number of ways to have the number of bit strings of length n plus 1 that have exactly k ones. Okay, so imagine we have a bit string of length n plus 1, and there are exactly k ones. Well, I can ask myself, for instance, is this a 1? So I can take my string and break it into a string of length n and just this one right here. And so I can ask, is this one a 1? If it is, I now have k minus 1 of these remaining spots to be 1s, right? So that gives me the n choose k minus 1. Or if this is not a 1, then I need to add the number of ways to have exactly k of these n slots be filled with 1s. So what we're essentially doing is saying this right here is the number of ways to have exactly k of the first n terms be 1s, right? So last term is a 0. Plus, this is going to be the number of ways to have exactly k minus 1 of the first n terms be 1s. So the last term is a 1. So we're using the addition rule. Because we're saying if you're trying to build a string, you're trying to see how many different ways can you build strings of length n plus 1, right? You can just ask yourself, well, if I have a string of length n plus 1, then I've got the first n spots, and then I have the last one. Either the last one does have a 1, or the last one does not have a 1. If that last spot has a 1, now I just need to count the number of strings of length n that have k minus 1 ones, okay? If the last string is a 0, then I need to count the number of strings here where exactly k of the terms are 1. And then the total number with length n plus 1 will be the sum of these two because we have two disjoint subsets there. Okay? So that's a combinatorial argument for why Pascal's identity is true. And the last way I want to show you is using what's called Pascal's triangle, because you can kind of see, based on the argument that we did before, we said, hey, if you have an n plus 1 length string, That's really just a string of length n, and then you tack on another piece, right? So you can build your string of length n plus 1 by considering strings of length n and then thinking about what are the possible options for adding on another bit at the end, okay? We do exactly the same thing here. So look, if we're looking at the product x plus y to the 0th power, that's just 1, x plus y to the 1th power, to the first power, that should be x plus y. I'm looking at the coefficients, 1 and 1. X plus y squared, 1x squared, 2xy, 1y squared, yes? X plus y cubed, 1, 3, 3, 1. The thing to notice about Pascal's triangle is that the way you get the next row is by adding directly above and to the left. So to get this number here, it's going to be 5 plus 1, which is 6. To get this number here, I'm going to get 15 because I'm going to add 20, 15, 6, and then a 1, right? And it goes on and on, goes on and on forever. So Pascal's identity is saying n plus 1 choose k is the same as n choose k minus 1 plus n choose k. So if I want to get say this, which corresponds to, what is this, 5 choose 2? Right, 5 choose 2. I get it from 4 choose 1 plus 4 choose 2. So if I'm looking at this in terms of my